Hello, well, we're going to be doing checkpoint 5.19. In this checkpoint, they want us to evaluate this double integral. It's r squared times sine squared theta r dr d theta. So it looks like it's already in dr d theta. There's no need for transformations from Cartesian to polar. And in fact, it looks like the r is already kind of built in. Here we have our region is going to be given by, well, it's already given to us here, so we can just write r. It's going to go from 0 to this function. We have 2 this times the square root of cosine 2 theta, and then theta goes from minus pi over 4 to pi over 4. And I think if you were to graph this, it'll look a little bit like a lemniscate, which is like a figure 8 or figure infinity. But I don't think we need to mess with that too much. All right, and so if we set up this integral, we're going to get the integral, and let's do the theta first because it's constant, and by first I mean the outside. So let's do the theta on the outside, minus pi over 4 to pi over 4. The outside integral, the integral is r going from 0 to 2 square root of cosine 2 theta, and the integrand is going to be r squared sine squared 2 theta with an extra r, and then dr d theta. Yeah, so if this this looks like a y squared here, and then this looks like a dA. So if this r would have been nicer to change into Cartesian coordinates, I might have been tempted to change everything into Cartesian coordinates and integrate that way. But this expression here, it's not easily changed into Cartesian coordinates, so I think it's better that we stick with polar, and everything's all set up here. It's just a matter of taking integrals. If we take the integral here on the inside with respect to r, actually we can do that trick again. No, we can't. So I was going to say, since these are all factors, we can factor them out. But here you have r as a function of theta. So we can't just take the theta out and the r out separately. So we have to be careful not to mess around with that. So we're actually going to take the integral with respect to r. We have r to the third. The antiderivative will be r to the fourth times 1/4. Okay, so now that we have that, we're going to evaluate this from 0 to this function. That's 2 squared root of cosine 2 theta, and when r is equal to 0, that just disappears. And so put that into the square root. 2 to the 4th power is 16, divided by 4 is 4. And then we have cosine, the square root to the 4th power is going to be squared, so that's cosine squared 2 theta. Okay, so that's your integral, the inner integral. And let's take the 4 out. So we will have a 4 outside, and we're going to integrate from minus pi over 4 to pi over 4 positive. And then we're going to have this function, and then we also have this function. So it'll be a sine squared 2 theta times cosine squared 2 theta d theta. Okay. Now for this, because these are even powers, we have to use half-angle formulas to solve for this. And we'll have a half-angle formula for the sine, half-angle formula for the cosine, and then you'll multiply them, and then you're going to get another squared term where you're going to need to use another half-angle formula again. And so that's that's calculus 2 work, and I think we should all be able to do that. But just to save time, let us take a look at the Wolfram version of doing this integral. And I'm going to share the screen that has this. And so this is what we have. It looks like the antiderivative here is going to be equal to 1 over 64 times 8 theta minus sine 8 theta. Well, that's just the indefinite integral, so why don't we just go ahead and go all the way through and evaluate this at the appropriate limits. So that's going to be negative pi over 4 all the way up to positive pi over 4. And if we do that, we're just going to get a value. So according to this, it's going to be pi over 6. So let's say that this whole thing is equal to pi over 6. Or I'm sorry, pi over 16. That's pi over 16. And then we also have that 4 that we're multiplying by. And so the total is just going to be pi over 4. Okay, so that's your result. I think that's it. Okay, I hope that helps.